Hi and welcome to this Leaving Cert Higher Level Applied Maths video. In this video, we're looking at the 2025 Higher Level Paper, Question 6, Part B. Students Anya and Brody are investigating the properties of an elastic resistance band in their school gym. The band has a natural length of 1 meter and an elastic constant of 650 newtons per meter. One end of the band is attached to a fixed pole. Use integration to calculate the work done by Anya in extending the band horizontally to a length of 1.2 meters. Okay, so there's two things going on in this question. The first is we're dealing with the fact that there is work. They've mentioned integration. So we have the integral of F ds, which is force, with respect to S, which is our displacement. Because we're dealing with this elastic resistance band, we're dealing with Hooke's law. So the force we're working with here is minus Ks. Remember that minus has just got to do with the fact it's a restorative force and we don't actually use it within the question. If that's a bit confusing, go back and watch the Hooke's law video and hopefully that will all make a bit more sense. So here is what we have. We have Anya pulling on this resistance band. It has a natural length of 1 meter. She has extended it to 1.2. That means our extra displacement X is 0.2 meters, and that's what we want to work with. So let's get this set up. So work is equal to the integral of F ds. Our F in this case is the force due to Hooke's law, which is Ks ds. So if we want to actually go and do that integration, that becomes Ks squared divided by 2 plus a constant, but we can ignore the constant for now. If you want to use our limits, the displacement is going from 0 to 0.2. Remember, S is the displacement or the extension beyond our natural length. And our natural length, just to point it out again in the question, our natural length is 1. So it's extended by 0.2. So that means when we get to here, we're looking at subbing in 0 and 0.2. We also have a value for K, so you could have put that in earlier. Does not impact when we put that in, so that's 650. So that's going to give us work is equal to 650, 0.2 squared divided by 2. And that all works out as 13 joules. So part 2, Brody takes the extended band and extends it further. He claims to have done twice the work Anya did. If Brody is correct, calculate the new length of the band. So Brody is already starting with the displacement of 0.2 when he is doing his stretch, and that's important. So if we go back to our formula, we'll put in 650s ds, and we know this time that he's claiming to have done twice the work, which is 26 joules. And when we do our integration here, that's going to be 650 s squared all over 2. Now, in terms of our limits, that's going to have started at 0.2. And that's really important because he started at 0.2 and he goes to some limit that we don't know. So 26 is equal to 650. Let's go between 0.2. Let's put an x in there instead. So x squared all over 2 minus 650, 0.2 over 2. We know that that second fraction is actually 13. So we can just do a minus 13 here because that was the same fraction we actually had in part 1. So bringing that over, that gives us 39. So we get 650x squared. Actually, let's make that easier, 325 rather than a fraction. And that is equal to 39. X squared is equal to 39 divided by 325. That gives us the extension he does, square root of that. And that gives us an extension of, so square root of 39 over 325, and we get 0.35. So the length of the band is going to be the natural length plus that, which is 1.35 meters. So what was tricky there is remembering that Brody starts at the zero point 0.2 of a displacement. He doesn't start at zero. I'm going to look at an alternative method for this. In the exam, it did say use integration. However, anytime we're doing any question about work or specifically about integration, we can deal with the idea of graphs. So let's look at how graphs could be used. Again, the question did say use integration. So if I were in an exam, I would use integration. But if the question didn't say that, it's good to know how we can explore graphs and how they might actually work out better. Some people find it easier when they can visualize. So we're still going to need our two formulas. They are basic. But if we were thinking in terms of a graph, we can think of our force versus displacement. So here's my graph for Anya. So when we work this through, we think of the area under the graph as work done. So remember that integration is that area under the graph. So when we work this through, we could get Anya, which her work is just going to be a half times the force times displacement. So that gives us, if we think of force as our Hooke's law, so Fs, that gives us a half times 650, which is our K times S times S. So that works out very nicely as our 13 joules. It still is, if you looked at that formula, a half K times displacement squared. So it works out the same as if we had integrated it. So then when it comes along to part 2 for Brody, we can simply extend that line. So if we think of again the area under the graph as work done, to simplify this, let's look at the total area, including Anya and Brody, so that would be 3 times work. So we have Anya who did 13 joules of work, and Brody does twice the work, which is 26, meaning the total area is 39. So let X be the total extension. So that means half the force times displacement is going to be a half times 650 times X will equal my 39. Again, we end up with something kind of similar to what we had in using the integration, and working that through, that gets us to 0.346, and that is a length of 1.35. It's a nice little idea if you want to look at work done in terms of your graph. It's remembering that the integration is area under the graph. Now, somebody might say, could we not just look at Brody's on its own? Why are we including Anya's? So absolutely you can, but if you start working with Brody's on his own, it's a very complicated shape. Well, it's very complicated, but it's more complicated, especially given what we want to do. So we have to break it into two shapes. We have to think of it as the rectangle at the base and the triangle at the top. And we need to understand these 2 points. We suddenly now have two forces. So the area under the graph specifically for Brody is going to be the change in the force and the change in displacement, because we're not starting at zero. And we now have two elements to it. So it's going to be a bit more complicated. We have the triangle, which is a half, the change in force by the change in displacement. That triangle is just delta, which means a change. So it's the difference between force 1 and force 2. So force 2, take away force 1. Change in displacement, again, the same. We know that the first displacement is 0.2. We don't know the other, so we'll call that x. So this is what it turns out as. It's not very nice, it's not very pretty, but it actually all simplifies down to the exact same thing. So then when we work that through, we get the same answer. So if you decide if there's a question like this and you want to use graphs, absolutely do, but do try and work it the easiest way possible. If all we had were numbers, this would not be an issue. That kind of shape can be easily calculated. When we're doing algebra, when we're working backwards to find something that's missing, that's tricky. Think instead, can you be clever? Can you use the whole graph?